The name of the game is Calculus, and today we're going to use a calculator. So we're doing the second half. Numbers 29 through 36. This portion of the test you are allowed to use a calculator, but you'll notice that there's a lot of questions that you don't really need them. So let me go ahead and get my calculator started here. You should get yours as well. It's going to take a second to load up. While it's doing that, let's go ahead and look at the first question. So it says the average value of a continuous function on a closed interval 3, 7 is 12. Okay, well that's easy enough. When we hear the words average values, some things should be going off in our head. The first one that I think of is the general formula for average value. It's 1 over b minus a times the integral from a to b of some function. And right now they don't really care what the function is. It's just some general function f. But they did give us specific values for a and b. So let me go ahead and fill that in. It says the average value is 12. Notice that they told us that it equals 12. So we're going to say 1 over 7 minus 3 times the integral from 3 to 7 of f of x dx. They're going to say this equals 12. So that's what we're saying here, that it's equal to 12. So if I simplify this a little bit, that means 1/4 of this piece here equals 12. The integral from 3 to 7 of f of x dx equals 12. What's that really saying then? Because they're asking, the question that they're asking here is this. What's the value of that piece? So in other words, 1/4 of what equals 12? Well, the only thing that would fit in here is E, 48. Because anything else that I were to plug in, it'd be incorrect. And you've got to be really careful with fractions here. Some people really forget their basics with fractions, and what they'll say is, oh, 12 divided by 4 is 3. And they'll guess 3. That's probably the most guessed wrong answer, but that's completely wrong. Moving on, number 30. The region in the first quadrant enclosed by the x-axis, the line x equals pi, and the curve y equals cosine of x is rotated about the x-axis. What is the volume of the solid generated? Well, let's give ourselves some pictures because we love pictures. We start out with an x and y axis, so we know what we're looking at here, and we need to know what this curve looks like. That'll be interesting. Let's see what this curve looks like. Oh, I recognize those curves. Those are from before. Clear these out. Let's give you guys a view of what's going on. If I go up to my first y function here, oh, we got another one still to be cleared. Clear. There we go. Okay, to see what function we're having here, we have cosine of x. It's kind of weird. We haven't really dealt with this little embedded double cosine. By the way, let's change this view. Can we do that? I think if we go down to the next page here, we can view it in the classic version. Classic. I want classic. Why? Because some of you need to see what that looks like. Cosine of x. So when I go to graph this, I have this interesting looking graph that's going around there. I need to change my viewing window. I noticed that it said first quadrant, so I'm going to go from 0. It also said that I'm going to about pi. Pi is 3, so I'm going to go to about 4. And then it also said that we have just that one function between that and the x-axis. And if I looked at it, it looked like it was around 1 or 2. So and we're only going to the x-axis, so we can start at a bottom of 0 and go all the way up to 2, such a big number. Let's see what it looks like now. Ah, that's pretty. Okay, so we're going to be having a vertical line about here at x equals pi. When we see this right here, let's use some better colors. X equals pi is a vertical line. If it's a vertical line, then that means right here at pi, what I need to do is go ahead and sketch this. We have a curve, so it looks like it goes up and comes back down, almost like a little bump in the road. So it looks something like that. So this is our function. Here's our area. Let's go ahead and shade this green. So we're taking this area and we're going to take this entire area, we're going to rotate it about the x-axis and create a volume. It's going to be an interesting looking solid vase. So we need to ask ourselves a couple of questions because we're doing a volume of rotation. The first question, is it attached to the x-axis, or I should better say the axis of rotation? Right here, there is no empty space. It is attached the entire time. That means that the volume is going to be the integral from a to b of pi times big R squared. And big R is going to be the distance between these two edges from the axis of rotation to the upper edge here. So just to color that in, this is our radius. This is R. So what does it equal? Well, R is going to be the distance from that function to the bottom, so it's going to be cosine of x. And the integral is going to be an a. Let's go ahead and set those up. A equals 0. We start at 0. B equals pi. We go all the way up to pi. So our volume is going to be equal to pi times the integral from 0 to pi of cosine of x squared dx. Alright, so now that we have this piece, we just need to type that in and calculate it. Well, I have something I can do here. I have the original function. Why don't I just square it? So I'm going to do squared to the power of 2. I'm also going to multiply it times pi. So I'm going to insert a piece here, second insert, and I want to do pi. That's not what I wanted. I want to do second pi, and we're going to insert a multiplication symbol. So second pi times cosine of x squared. So that's our graph. That's our function actually after we've made all the adjustments. I don't care that it looks differently now. I should expect that. But what I want to do now is find this integral from 0 to pi, because that's what it, even though it doesn't look like it used to, that's the calculation that I need to find. So I do second calculate, then I'm going to calculate the integral, number 7. And the lower limit is 0. The upper limit is pi. Type it in. The answer is 6.03. Is that one of my options? Hey, this looks close enough. Next. Number 31. Ooh, we went off the page here a little bit. Let's pull it back up. It says if f and g are piecewise linear functions whose graph are shown above. This was originally above, but now it's below. But it's the same thing. If h of x equals f over g, then h prime of 3. There's a classic mistake that most people make here. They plug the number in, then they take the derivative. Not cool. Not supposed to do it that way. Because if it's asking for h prime to 3, I don't even know what h prime of x equals. The other classic mistake is they see a quotient and they forget the word quotient and they think that h prime of x equals f prime of x over g prime of x. Whoops, that's not another g. G prime of x. Not true. You know this. Keep it simple. So if we're going to find h prime of x, it's actually going to treat this like a quotient rule. Low d high minus high d low. So low d high minus high d low over low squared. So low d high. Low d high is going to be g of x times the derivative of the high, which is f prime of x minus high-D low. We're going to invert those a little bit there. So now we have f of x times g prime of x. Now on the bottom we got the low squared, so it's g of x squared. So let's do some color coordination here. Let's start out with the g's. I'm going to have g of 3 and g of 3 squared. So I need to figure out what g of 3 and g of 3 squared is going to be. So g of 3 equals, okay, let's see, g of 3. That means I look at the function g, and I go to 3, and g of 3 equals 3. That was easy enough. I should cover up this piece here with a different color. How about black? There we go. And let's do another color now. How about red? For red, we'll do f of x. So I'm going to do minus, and we got f of x. So f of 3 f of 3, which means I just plug in 3, and I go to the f function, is 1. That's easy enough. Now for these next pieces, this is where it gets a little bit different and people might not be paying as much attention. When I'm finding f prime of 3, what is that actually asking me to find? F prime of 3 is the slope of f at x equals 3. Let's figure out what that is. The slope of f at x equals 3, I'm here at 3, but my slope, it's a constant slope, notice. That's why these are piecewise linear functions. My slope is negative 1/3. And for the other one, final color, we had blue. Let's do we have purple? How about let's make a purple in here. So purple, g prime of 3, similarly is the slope of g at 3. And if you look at this, that's a very simple slope. That's just 1 over 1. So it's just 1. So g prime of 3 is here. And, oh, did I change? No, here we go. Orange f prime of 3 is here. So I'm going to fill in these pieces now so you guys can see what we're getting. F prime of 3 is negative 1/3. F of 3 is 1. G of 3 is 3. And G prime of 3 is 1. And then we also have that G of 3 on the bottom, so it's going to be 3 squared. So we've got to just calculate all this. So we have 3 times negative 1/3, so that's negative 1. Minus 1 times 1, that's just 1. Negative 1 minus 1 is negative 2. On bottom we have a 9. Negative 2 over 9 is the answer. Next, number 32, the region bounded by the x-axis and part of the graph y equals cosine x between x equals 0 and x equals pi over 2 is divided into two regions at the line x equals c. If the area of the region is equal to the other region, then c must be. So what are we even talking about here? Let's give ourselves an idea. So first, x-axis, we got a y-axis. What's so cool about this question is I have a graphing calculator. So I'm going to go back to my y equals. I'm going to change this function to simply cosine of x. I believe that our window is now from 0 to pi over 2. So we'll do pi over 2. You can actually type this in and it will do it for you. It will approximate it for you. 0 to pi over 2. And if I go to the graph, that means I have this function here. So what it's saying is somewhere here in the middle, I will split this area into two equal pieces. So right here, let's say I was at like 0.65 or something. Then that would tell me that I would have two equal areas on the left and the right. So we have a curve. I'm going to go ahead and draw that curve. It looks kind of like this-ish. Not exactly. I know it didn't curve straight down. It was more slanted, I guess. So we're looking at some point C in the middle. That's probably not it. It's probably more over here, actually. Let's go ahead and erase this other one. And we want this blue area to equal this red area. That's what we want to happen. So visually we understand what's going on by now, hopefully. But let's see if we can do this algebraically. Well, first we got the integral. And we're going from 0 to pi over 2. And we got a c in the middle. And this function right here is y equals cosine of x. So we need to go from 0 to pi over 2, cosine of x, and that dx. And that equals the total area. So then what I'm looking at, from 0 to pi over 2 cosine of x, I can almost do this by hand faster than I could with a calculator. The calculator just kind of helped me visualize what was going on a little bit here. So I take the antiderivative of cosine, that's really sine of x. I'm going to evaluate it from 0 to pi over 2. When I plug in 0, that's going to give me 0, so the bottom's going to give me nothing. When I plug in pi over 2, sine pi over 2 minus sine 0. 0 for sine of 0, sine of pi over 2 is 1. 1 minus 0 is 1. Piece that's changing. So again, I have cosine of x dx. I know that that's really sine of x, and we're evaluated from 0 to c, and I know that sine of 0 is going to equal 0, so I know that that part doesn't really change anything, but here I'm going to have sine of c. Sine of c then. And what I need to somehow figure out is how do I make this c come to a position such that this area is half and this area is half. And exactly, not just half of the total area, but if the total area equals 1, then half the area equals half. That was even easier. So we just need to figure out how do we make that equal half and that equal half. So sine of c minus 0 has to equal 1/2. In other words, sine of c equals 1/2. So what I'm trying to figure out is at what angle c does the function sine equal 1/2. So well, if I know my unit circle, we love the unit circle. Absolutely love it. So I have my unit circle here. I'm going to think about first quadrant, especially just because it's easier. Now if I'm thinking sine is equal to 1/2, that means that the y value is 1/2 of this triangle. So that means we're going to have a shorter triangle, looks something like this. So we got a short leg and a long leg, meaning that this angle in here is 30 degrees. If that's 30 degrees, think of that in radians. That's really pi over 6. So that's saying that sine of pi over 6 equals 1/2. That must mean that pi over 6 equals c. Booyah! Next. For what values of the function? Decreasing. Okay, so you could totally do this by hand again, but I'm going to use a calculator just to accelerate just a tiny bit. First, I'm going to take the derivative, because when I hear the word decreasing, that means that f prime of x is less than 0. The f prime of x is negative. Let's rewrite that. I know how to spell. The f prime of x is negative. Visually, that means it's below the x-axis. So if I have the derivative and I just graph it, all I got to do is look, when is it below the x-axis? Well, this is a simple polynomial. It's always continuous, therefore always differentiable, so we can always take the derivative of it. Derivative of the first term is 0, derivative of the second term is 15, third term is going to be plus 12x. We bring down the 2 to multiply by 6. Then we have minus 3x squared. This is my derivative. Let's graph this derivative. So we have a new function here. We're going to change our window. Actually, zoom, standard, y equals, and then we have 15 plus 12x minus 3x squared. So easy. Look at this graph and you tell me, when is it negative? Well, it's negative when it's below this x-axis. It's right here before 1 and right here after 5. Only one of these says before negative 1, I should say. This says before negative 1. And it also says after 5. D. A D. A D. If f is an antiderivative of this, such that f of 1 is 1/2, then f of 0 equals, ooh, this is interesting. What it's saying is that f equals, or f of x equals the integral from 0 to x, let's say whatever, g of x, and f of 1 equals 1/2. So that means the integral from 0 to 1/2 is equal to 1. F is an antiderivative of this. Oh, so that means that this is our little g of x. So that means we have to take the antiderivative of that. Wow. Okay. Let's do this. Oh, I see what's going on. If we have tangent of x over, and this is squared, we got x squared plus 1. Well, I know that the integral, the antiderivative, or let me put it this way. If I have the integral of 1 or du over a squared plus u squared, that's going to be, oh, this is a, I want to say 1 over a times arctan of u over a plus c, of course. So what I'm looking at here is that if I have tangent in x squared plus 1, no, I think I'm actually going to have to come back to this one. But let's see, let's think about this for a second. We know that f of 1 equals 1/2. F of 0 then, what's the integral at 0? Let's go ahead and plot to see what we get. We're going to have, clear, we got tangent squared, tangent of x, and we're going to close it off, then we're going to square it. We're going to divide that by, now we've got to put this in parentheses, x squared plus 1. Let's see what that gives us. So we're trying to find the area under this curve. Let's say that I found the area from 0 to 1/2. Or not from 0 to 1, from 0 to 1. So let's do second, calculate the integral, which is 7. The integral from 0 to 1. That equals about 0.34. And up here, this is giving, oh, that's interesting. This is saying from, that f of 1 is 1/2. That means that this is not from 0 to x, this is from a to x. That means that I need to have this go a little bit further back, okay, for that to equal 1/2. Let's say that I went from -1 to 1. So if I do the integral, second, calculate, the integral from -1, whoops, wrong thing, second, calculate, 7, we're going from -1 to 1. That gives me about 0.68. If I were to calculate this even more specifically, let's say I'm going from second, calculate 7, let's say I went from 0.5 to 1. I need to delete that. Delete. That gives me 0.304. Oh, that's kind of weird. Let's say I went from -0.75. Second, calculate the integral of my lower limit. I'm going to do -0.75 to 1. That gives me about 0.48. So I need to go a little bit further. Then I'm going to do second, calculate, from -0.8 to 1. That gives me about 0.51. That's probably pretty close there. So that's saying if I integrate this from -0.8 to 1, then I get that. So then I need to figure out what's the integral from -0.8 to 0. So if I do from second, calculate, and I'm going to integrate from -0.8 to 0. That's about 0.165. The closest thing that I would say to that is B. So that's the answer that I'm going to go with there. Number 35, the second derivative of a function. Let's get something a little more straightforward here. Second derivative of a function is this. How many points of inflection does f have on the interval 0 to 20? Ooh, this is interesting because it's asking a very straightforward question. All you have to do is know how to interpret it. Well, we hear points of inflection. A point of inflection happens when f double prime, or the second derivative, changes sign. Because that indicates that we change concavity. We go from negative to positive or positive to negative. And then the point of inflection is that point in between where it changed. So let's look at this function over this interval. We're going to go ahead and type this one in. This is a lot more straightforward here. Way more straightforward. So the function is 0.05 or 0.5, pardon me. So y equals 0.5 plus cosine x minus e. Now e is with the natural log function over here, so we're going to do second e to the negative x and we close that off. Let's see what we get. Oh, we need to change our window. We're going from 0 to 20. Time to graph. So I count 1, 2, 3, 4, 5, 6. Did I type that incorrectly? So we have 0.5 plus cosine x minus e to the x from 0 to 20. Let's zoom in just a little bit just to make sure. So I'm going to change my y values. Instead from -10 to 10, let's do -5 to 5. so we definitely have 1 sign change, 2 sign change, 3 sign change, 4 sign change, 5 sign change, 6 sign changes. Wow, 6. Number 36, the local linear approximation of a function f will always be greater than or equal to the function's value if, for all x in the interval containing that point of tangency. Okay, so what's happening here? It's saying that the linear approximation will be greater than. What that's meaning is that we have a curve and a tangent line. And for that tangent line to always be greater than in some interval, let's see what needs to be happening. So let's start with a couple of curves. We have 2 basic ideas. First, we have just a curve that's like this. We also have a curve that's like this. We could even have a curve that's like this. Whoops. Take that one back. We could have one that's like this. Or one that's, oops, let's not do that one. Let's do this one. There we go. So we got those 4 options. It almost looks like a little guy running. Do you guys see it? I see it. Here's his head. Take that one back. Okay, so right here, let's see what's happening. This tells us, in this one we know that the slope is positive and the concavity is negative. In other words, that's saying that f prime is greater than 0 and f double prime is less than 0. Here we have slope negative, so that means f prime is less than 0, and concavity up, so f double prime is greater than 0. And here, for this one, we have f prime is greater than 0. Why? Because the slope is positive. It's going up, 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 just like that. It's greater than 0. F double prime is concave up. It's concave up, so therefore it's greater than 0 as well. And then this last one, we have a negative slope. F prime is less than 0, but it's concave down, so it's also less than 0 for the concavity there. So we're looking for tangent lines, straight, flat lines that are above. So this tangent line, let's say I'm at this point here, this tangent line approximation is going to be greater than because it's sitting on top of the curve. This tangent line is going to be less than, and so is this one here. But this one's going to be greater than. So what makes the difference? Why are these two that I'm about to highlight here, these two right here, how come those are greater or above? And why are these two in red less or below the line? Let's see what these things have in common. This one has a positive slope, this one has a negative slope, so that's definitely not in common. Those things are different. But they're both concave up, and then if you look at that's kind of the consistency with the second one. These are both concave down, and these other ones are both concave up. In other words, if you're concave up, your tangent line is always going to be below, and if you're concave down, your tangent line is always going to be above. Because that's what a local linear approximation is. It's just a tangent line and using that tangent line to approximate. So which one of these, if we're saying is greater, this one our tangent line is less. If we're concave up, if we're concave down, it's greater. So we want concave down, therefore we want f double prime less than 0. C. Number 37 through 45, we're at the end here, the last 9 questions. Let f be a function given by, wow, that looks complicated. F is increasing most rapidly when x is, wow. So it's saying, when is it most increasing? That's kind of interesting, because that's saying when is the greatest positive slope. Well, the greatest positive slope is going to be the greatest derivative, or the max of f prime of x. Well, that means we're looking for the max of f prime of x. That's what we need to look at. So let's start with this and then work our way from there. If I look at this function, first thing that I want to try and think about doing is trying to find the max of the derivative. Well, I can actually use my calculator to graph a derivative. So let's start with the original function. Scroll down here a little bit so we can see it. Go back to y equals. Clear this one out. We have 5. Whoa, this is going to be a little bit hard. Let's shrink down this calculator. Oh, that's as low as it goes. We have 5 plus 5.8 times sine. Now in here we have second pi x divided by 4. We have minus 15.7 cosine. Now in here I'm going to have pi x divided by 3, so I have second the pi times x divided by 3. So let's go ahead and graph that. Actually, how far do I want to graph it? Looks like the lowest x value I need is 1, the greatest one is 10. So let's see what we can calculate here. Our window, we're going to be going from about 0 to not 20. Let's go from 0 to about 11 and see what we come up with. Now my y's, I don't know where those are going to be yet, but let's see what we're looking at. Whoa, we are all over the place. Wow. Well, I could go into the derivatives and try to figure out when we're going to optimize that, but there's another way that I can calculate this. I can calculate each of these slopes on my calculator and just figure out when it is the greatest slope. When is the slope increasing? F is increasing most rapidly. So it's saying which slope is greatest. So let's calculate the slope at 1.328. Second, calculate the slope, which is dy dx, at 1.328. That's about negative 19. I don't think that's going to be it. So the slope here is negative 19. Let's look at the next one. Calculator. So we're going to do second, calculate the derivative or the slope at 4.434. When I calculate that one, I get about 13. So 13. Next one. And then we have second, calculate the slope, which is 6. And we're going to calculate at 6. We get 0.03, so that one's out too. 0.03. That slope's pretty slow as well. It's not increasing a whole lot. And then we got 7.566 for the next one. Second, calculate the derivative at 7.566. Type it in, you get wow. Wow. That's a big slope. I think that's going to be one of them. But the only one we got to check now is 10.672. So we got second, calculate the slope at 10.672, negative 67. So the winner is, which one has the greatest slope? Ding. Next. If the limit as x approaches 3 of this equals this, then near the point where x equals 3, the graph of g of x is, one of these. Well, what is this actually saying? We know we have a couple of versions of something that goes on here. The first thing is we know that the limit as x approaches, or let's even start this over. Completely start it over. We'll write in blue. The limit as h approaches 0 of f of x plus h minus f of x over h equals the derivative. This is the limit definition of derivative, but there's another version of it. We're looking at the limit as x approaches 3 of g of 3 minus g of x over 3 minus x. That also equals f prime of x. How do I know this? Well, this is really just slope formula. We got y2 minus y1 and x2 minus x1. So we're looking at slope, but this slope is becoming so instant. We're going from 3 to 3, basically. So we're looking at the instant at 3, the instant slope, which means the derivative. And it's saying that f prime is approximately negative 6.28, or negative 0.628, pardon me. Negative 0.628. That means that the slope is negative. If the slope is negative, it's definitely not increasing. Maybe it's concave upwards, maybe it's concave downwards, but I don't even know. Maybe it has a point of inflection. It could be one of those, but I definitely know that it's decreasing. These are possibilities, but I definitely know it's decreasing because slope is negative. Next. Here we go. Number 39. How many zeros does this function have between 0 and 1? Notice this. That's interesting because the first one did not include 0. Why? Because we can't do natural log of 0. It doesn't work. It'd be a limit, and it's approaching infinity, so it doesn't really exist. But we can include 1. So let's go ahead and graph this function and see what happens. So we're doing sine of natural log of x. Let's go ahead and erase this big messy function. Clear. We got sine of natural log, which is over here, of x. Graph it. Oh, what is our interval? I didn't even think to look at that. We're going from 0 to 1. Ooh, we got to zoom in here. Let's go from 0, not to 11, but just 1. And negative 5 to 5, that looks good. Let's go ahead and see what we get. Okay, so I definitely have a 0 here, but then the question is, do I have a 0 there? And that looks like it's going all the way to 1. I want to zoom way in just to see. So let's check that out. That means that I'm going to have my x or my y values. I'm going to zoom way in. We're going to go to like negative 0.1 to 0.1. And I want to look right around 1 as well, because I know it hits earlier, but let's see if it hits right around 1. If I do 0.8 to about 1.1, let's check this. Does it cross? Yes, it does, right here. Let's double check that again. So if I go to the window, I'm going from, whoa, whoops, I totally have the wrong one. So I'm going from 0.8 to 1.1. Down here my scale, I'll do 1. Does it cross? Does it cross? Does it cross? Yes, it does! It totally crosses at 1. How many zeros does it have? It has 2. Now, if I wanted to confirm that algebraically, I want to try and set this equal to 0 and see what I can figure out. Well, then that would be asking, when does y equal 0? 0 equals sine of natural log of x. When does sine equal 0? Well, it equals 0 at a couple of places. So that would be asking, when does sine equal 0? It's going to equal 0 at 0, of course, and at pi. So then what I'm asking is, does natural log of x equal 0? And does natural log of x equal pi? or negative pi, for that matter. We know that this is meaning x is going to equal 1. But we saw that that other 0 was somewhere between like 0 and 0.2 or something like that. So that's where we get our 2 zeros from. Let's look at number 40. We got 6 questions to go. 40, 41, 42, 43, and 45. Let f of x equal this. Let g be the inverse of the function of f. What is the value of g prime is 0? Okay, so this is something that we haven't really worked on a whole lot. It has to do with inverse derivatives. And for an inverse derivative, if g equals the inverse of f, and we're trying to find g prime, it's actually going to be a little formula. G prime is going to be equal to 1 over g of f, or f prime of x. Look this up just to check it right here, or it's f of x, pardon me, we got that a little bit backwards. So this right here is going to be g prime of f of x. Because what we're looking for is f prime of f inverse of x. Did I get it right? Looks like we got it right. No. G prime is 1 over f prime of g of x. Well, let's see what we can figure out from this. F prime, we can figure out f prime of x. That's not too bad. F prime of x is going to be 3x squared minus 14x plus 25. But g of x, g is the inverse. And what that's asking, when you're asking about an inverse function, so g inverse of 0 means when does f of x equal 0? So we need to actually plot that and then figure out that value. So when does f of x equal 0? So let's go back to our functions here. And f of x is this big, long polynomial. So I need to type that in. It's going to be x to the third power minus 7x squared plus 25x minus 39. Do they give us an interval? No, it just says find the 0. So I need to graph it. Probably need to change my window though. So let's do just a standard zoom. Get a general idea, see if we can get it from there. Well, it looks pretty clear. It looks like it hit 0 right around here. It looks maybe right about 3. There is a way to confirm that though. If I do second calculate, and I'm going to calculate the 0. Left bound, let's say from 2. And right bound, we're going to say 4. Because we know it's somewhere in between there. And I'm going to guess that it's about 3. Hey, it is on 3 because when x equals 3, y equals 0. So f of 3 equals 0. That means g prime of 0, or g of 0, I should say. G of 0 is equal to 3. Because inverse functions just invert the x and y. So f of 3 equals 0 means that g of 0 equals 3. So I'm looking for g prime of 0 is equal to 1 over f prime of 3. So I got to plug in 3 into this derivative. Well, let's just go ahead and figure this out because it's in some fractions here. It's probably going to be one of these here. That means we got 3 times 3 squared minus 14 times 3 plus 25. So this is 27. 14 times 3 is going to be 42. 27 minus 42 plus 25. So we got 27 and 25. That makes 52. Minus 42 is equal to 10. So the answer is actually the one that I'm covering up here. And it's 1/10. Wow, that was a lot of work. But this is the general idea that g prime of x, if f inverse of x is g, then g prime of x is equal to 1 over f prime of g of x. Easy enough. For all x greater than 0, if f of natural log of x equals x squared, then f of x equals. Wow, that's interesting. It's saying that x squared is what I get when I plug into this piece here. So when I plug in natural log of x, I'm going to get x squared. Then what's f of just x? Well, what I need to do then is EIFI the x piece in here. So let's say natural log of x is going to be my input. Well, what I'm going to do to my input, though, is I'm going to raise it to the power of e. Then that means I'm going to have this piece here. F of natural log of x is equal to x squared. Then f of e to the natural log of x is going to be e to the x squared. And f of e to the natural log of x is the same thing as f of x. But I'm not seeing that on any of these here. So I'm making a mistake. Let's see what we're trying to figure out. F of natural log of x is equal to x squared. Then what's our original function, f of x? You know, as we're looking at this, let's go ahead and take a fresh look at it, because it's kind of hard to do the algebra. It's like we don't have enough knowledge about the original function, but we do have something that is to our advantage. That's that the answer's somewhere in here. So let's look through the answers and see what they would be. Let's say that f of x was e to the x and square rooted. Then if we were to plug in natural log into that, then that would be f of natural log of x is going to be the square root of e to the natural log of x. And e to the natural log is going to, reduce, and then we got square root of x. Well, that's not what we need. We need x squared. So this one is out. Then we go to the next one. If we say that f of x is equal to 2 times the natural log of x, then that means that f of natural log of x is going to be equal to 2 times natural log of x. And this is not going to equal x squared. There's no way that'll work. We're not going to have that undo itself. It's probably going to be something with e. So I'm actually going to jump ahead and say it's probably not going to be d. Let's check c and e. So first we check c. We have f of x equals, first of all, these are questions. We don't know. We're checking. If f of x equals e to the square root of x, then f of natural log of x is going to be equal to e to the square root of natural log of x, or natural log of x to the 1/2. So we can take this square root and just make it a 1/2 power. Let's go ahead and do that. We're going to have natural log of x to the 1/2. Well, then that would mean that we have the e in the natural log reduced, and we just have x to the 1/2. That's not what we want, so it's not c. By default, then it's probably going to be e, but let's double check. F of x equals e to the 2x. That would mean that f of natural log of x, if we plug natural log of x into this, would be e to the 2 times natural log of x. Hey, this does work because the 2 will pop up, and that means that we're going to have e to the natural log of x squared, which is really just x squared, and that's what we wanted. So f of x was e, which is e to the 2x. And next. A rectangle is to be inscribed in a semicircle with radius 8, with one side lying on the diameter of the circle. What is the maximum possible area of the rectangle? This is a classic question. It has been used before. Let's go ahead and take a look at what we're looking at here. So we have a semicircle. Move this up. This semicircle is going to have a flat line underneath it. We know that it has, it has a radius of 8. So that means from here to here that this is 8. And if this is a semicircle, we know that x squared plus y squared equals r squared, x squared plus y squared equals 8 squared, so that y squared equals 8 squared minus x squared. So y equals the square root of 8 minus x squared. So that's my function here. And that's going to come into play in a second, because if I put a box, a rectangular box, inside of this circle, I need to find the area of this box. Well, the area of any box is base times height. So here's our height and here's our base. And strangely enough, our base is x on each side, so base equals 2x, and our height is equal to the function of the curve, which is f of x. And our area then that we need to maximize is going to be 2x, which is the base, times f of x, which is this here. So I need to max this. You max it. No, I'll max it. Let's max it together. We have a calculator that does all this cool stuff for us. So we're going to type in this function, and then we're going to maximize it. So let's start with the first part of the term. It's got 2x times the original function, which is the square root. We have a button on here that does square root. Second, square root. And then in here we got 8 squared, which is 64, minus x squared. X squared, close it off. Let's see what we get. So I need to maximize this function. Now I can't be less than 0 for x. I got to start at 0 or greater. So let's see where I'll be then. If I take this window, and it looks like this area is pretty big. I'm going to start at 0. Let's go to, I don't know, 20. No, the maximum. What would the maximum be? The maximum would be 8 for x. And then for the y value, though, because that's going to be really big, let's go from 0 to like 100. Let's see what we come up with. So there's my function, and it hits a max right about here. You see that? Right about there, we hit a max. So I need to figure out where that point is. Good thing I have a calculator. Second, calculate maximum for left bound. That looks good. And let's go to about 7 for the right bound. And guess, I don't know, 5.5. Boom, 5.65. That was a pretty good guess, actually. So now I'm looking at these ones. I'm like, oh my gosh, which one of those equals 5.65? Well, it might be 4. It's definitely not 8. Definitely not 32. Oh, what is the maximum possible area? So that's x. X equals 5.65. What I'm looking at then is the y value. Let's take another look at that. The y is 64. Haha. There we go. The maximum possible area is 64. That's interesting. I bet that has something to do with the radius being equal to 8. if f of x is e to the negative x plus 2 is differentiable at x equals 0, then a plus b is. If this is differentiable, that's not just continuous. It's not just continuous. It's also smooth. In other words, no sharp points. If you don't have any sharp points, we're smooth. And if something's smooth, that means that the derivative is also continuous. Well, let's see what that means. We have this function up here. We're going to take the derivatives of each one and make sure that those are continuous at 0. That means that the left has to equal the right. Well, the right side is going to be ax plus b. The derivative of that is a. And the left side is e to the negative x plus 2. The derivative of that is negative e to the negative x. And we notice that this is going to be 0, so negative e equals a. Actually, negative 1, pardon me, because negative e to the negative x, e to the 0 equals 1, and that's going to be a negative 1. So negative 1 equals a. To find b, we got to make sure that these equal each other. So e to the negative x plus 2 equals ax plus b. But x equals 0. So we're going to plug in 0 here and get 1. We're going to plug in 0 here and get 0 plus 5. 1 plus 2 equals, or not plus 5, that's a b. Wow. It's getting late, guys. Okay, ax plus b, 1 plus 2 equals b, b equals 3. Negative 1 equals a. A plus b equals 2. What was the key point in all that? Knowing that it's not just continuous, it is continuous such that the left side equals the right side at 0, but also that it's smooth and it's not scratchy. It's smooth. At how many points do the graphs blah and blah intersect? Wow. Well, let's graph them. We got 5 plus x to the 4th. We got 5 plus x to the 4th. I'm going to guess it's just 0, 1, or 2. I don't think it's going to be more than that. 5 plus x to the 4th, it might even be to 0. We have the graph 5 plus x the 4th. And we're going to delete these pieces here. The other one was point something something something. 5e. So we're going to do second. We're going to use e to the 0.2x. And let's graph those. Whoa, we need to look closer to here. So let's start by looking between negative 1 and maybe 2. So maybe negative 2 to 2, so we'll go from negative 2 to 2. And we clearly need to be closer down to 0, so let's go from 0 to like 6. Whoops. 0 to 6. Oh, looks like they intersect twice. Let's raise that window up to about 7 just to double check. Once, twice. The answer is C. We love graphing calculators on the graphing calculator part of the test. The line y equals mx plus b with b greater than 2 is tangent to the graph of this at a point in the first quadrant. What are all possible values of b? So in other words, it's saying that it's tangent to this graph at a point in the first quadrant. So let's graph this in the first quadrant. So when we graph that in the first quadrant, we got negative 2, negative 2 times x minus 2. We're going to square that. And we're going to add 2 to it. delete, 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 delete. So then if I'm looking at this, I get delete that. I'm going to graph it. We're just looking in the first quadrant, so that means we're way over here. So let's go to that. That means we're going to go from 0 to, let's say, 10. In the first quadrant, 0 to 7. That works for me. This graph goes down below, so I need to see what's happening below the axis as well. For the y minimum, then I will change that to -10, and this one will change to 7. We'll change that to 10 as well. Actually, no, we'll change that even lower. So we went to 7, and that's a little bit high. How about -10 to 4? All right. So here's the interesting thing. It's asking what are all possible values of b? B has to be greater than or equal to 2. That means that we have to have a y-intercept at 2 or higher in this range. And for us to be tangent, can we be tangent at 2? Oh, you betcha. Can we be higher at tangent at 2? Yes, we can. In fact, I'm going to take a picture of this just so you guys can see what we're really looking for. We need to take a picture, so let's take a picture. I'm going to take a picture of this to the current page and see what happens. So on my calculator, if I'm looking at the possible values for b, I need to have like a diagonal line here. If I'm at 2, I can definitely have a tangent line that touches there. I just have to remember that b has to be greater than 2. So I could do another line, let's do like a blue one up here, let's say it was 3. It can be greater than 2, and it can keep going up all the way up here, and I can still have more tangent lines hit right about at that point. And it's probably saying, can I go all the way up as high as 20? Well, I don't know. I think I probably could, because even if I'm way up here, I'm looking at this graph. This is just a quadratic. It's going to go way down there, and it can go all the way up. What are possible values of b? I'm sure that I have a slope that could be as much as 20. Because it doesn't really matter what the slope is going to be. It matters that b could be all the way up to 20. What are the possible values of b? I'm going to say for sure it's E. And that's it. We are done for the day.